Airplane designers will tell you that the wing is the heart of an airplane. For conventional airplanes, it provides most of the lift generated by the airplane. The fuselage and tail contribute only a few % of the overall lift of the airplane. The aircraft wing has transformed from the wooden and fabric twin-wing set of the Wright brothers flyer to the composite materials used in the latest models coming off the production line today, from the likes of Boeing and Airbus. In fact, Orville Wright's first flight lasting 12 seconds traveled 120 feet, less than the wingspan of a Boeing 747. The basic forces acting on an aircraft are thrust, drag, lift, and weight. OEMs are today placing a major focus on trying to reduce drag and weight across all components, in an effort to improve performance and efficiency. Hello everyone, and welcome back to the channel. Today we'll tell you all about the evolution of aircraft wings and how they've evolved since their inception. But before, make sure to subscribe to the channel for more similar content. Let's dive in. While the basic aerofoil shapes laid out in the 1930s by NASA and its predecessor NACA have remained the fundamental platform for generating the lift component, there have been huge advances in both the materials and manufacturing processes used. Efficiency is at the front of airline executives' minds. As an increasingly demanding customer base calls for cheaper flights, cost-effectiveness in both the operation and manufacturing of the aircraft is crucial for today's airlines to maintain profit margins. As airlines constantly push their manufacturing suppliers to deliver more efficient aircraft, OEMs are turning to technology to drive improvements in wing design and manufacture, focusing on improvements in aerodynamics and reductions in component weight. The most tangible example to explain how plane wings work is when one extends an arm outside a speeding car's window. Holding the arm straight, one can feel the movement force changes as the direction of the arm does. Tilting the hand upward will lift the whole arm. Plane wings work the same way, but what exactly is the reason they make the plane fly? The most common way to explain how plane wings work is to use Bernoulli's equation, which focuses on fluid pressure and speed. However, it is a wrong assumption. Mathematically, the lifting force generated by the difference of pressure above and below the wing is significantly less than the opposite force from the plane's weight. So, how do plane wings actually work? Unlike what was commonly believed, the air passing the top of the wing does not meet the air from the bottom at the wing's end. The movements create small vortexes of air that can even be seen by window seat passengers if there's enough humidity in the air. The air flows towards the tail of the plane on the top of the wing and towards the nose of the plane on the bottom of the wing, hence constantly circulating around the plane. The lower pressure above the wing causes this circulation, and it will be counterclockwise if the wing moves towards the left and air flows over the wing towards the right. To balance this rotation, a counter-rotation of the airflow is set up over the wing, where the airflow circulates in a clockwise manner. This creates pressure differences from the top and the bottom of the wing. This pressure is also affected by other factors as well. The shape of the wing, the angle at which the wing is tilted from horizontal, the speed of the air flowing over the wing, and the viscosity of the air are factors that can lower the pressure around the wings. The same thing will happen if the movement happens in any other fluid, gas, or liquid. Thus, the viscosity should not be taken for granted, especially that it changes with altitude. Putting all these together will show how plane wings work and make them fly through one of the basic laws of physics. The plane flies because the wings push the air down, and the air, according to Newton's third law of motion, pushes it back in the opposite direction. As mentioned in the beginning of this video, the most familiar example is how the arm stretched out of the car's window moves. If the fingers are held straight next to each other, tilting the hand will change the whole angle of the movement and lift of pushdown of the arm. In the 1920s, airplane designers moved towards the use of thick airfoils. By the 1930s, efficient wing design exhibited large aspect ratios and thick airfoils. The famous Douglas DC-3 is an excellent example. With its aesthetically beautiful high wing aspect ratio of 9.14 and streamlined 15% thick airfoil, Thick airfoils had structural as well as aerodynamic advantages. A thicker wing allowed storage space for fuel tanks and retractable landing gear. A thicker wing also allowed a larger and stronger structural spar along the inside of the wing, which in turn allowed the wings to be cantilevered from the fuselage without any external support wires or struts. This helped to encourage the use of the modern single wing or monoplane instead of the older two-wing biplane configuration. With the advent of jet airplanes in the 1950s, pushing speeds close to and beyond the speed of sound, airfoil and wing shapes made another dramatic change. Thinner airfoils allowed subsonic airplanes to fly closer to the speed of sound before encountering adverse shock waves over the wings. Shock waves which greatly increase the drag and reduce the lift. For supersonic airplanes, the driving design feature was to reduce the strength of shock waves on the wings, and hence to reduce the supersonic wave drag. The thinner the airfoils, the weaker the shocks and the lower the wave drag. The Lockheed F-104, the first airplane to be designed for sustained speeds at Mach 2, is a perfect example. Types of aircraft wing can be characterized on the basis of their shape, position, and the number of wings attached to the fuselage. On the basis of shape, it can be an elliptic wing, rectangular wing, delta wing, boxed wing, dihedral wing, polyhedral wing, anhedral wing, gull wing, etc. On the basis of positions of wing, it can be a low winger, mid winger, or high winger. On the basis of number of wings, it can be a mono, biplane, triplane, and so on. What's a monoplane, you might ask, and you might wonder whether a plane can fly with one wing. Only if the wing is stretched from one side of the plane to the other, in a way that the plane is located in the middle, it can fly with one wing. This means, in the current technology and how plane wings work, it is impossible to fly with only one wing at one side. Losing one wing while flying is a disaster. Wing and airfoil shapes are still evolving today, driven by new and challenging flight conditions. The drive for more and more fuel economy in flight is driving new and better wing configurations and airfoil shapes to obtain higher lift-to-drag ratios. Also, future hypersonic flight vehicles flying at Mach 5 and higher will require innovative new wing and airfoil shapes, so the evolution marches on. That was all from us today. For more similar content, make sure to subscribe to the channel. See you in the next one.